Welcome, everybody. Today is May 11th, 2026, and we have the pleasure of a special presentation. It's part of our ongoing webinar series for the Web3D Consortium. The talk you're about to hear was first presented last year at the Web3D conference, and it's been very influential in our thinking and in how we proceed with the use of generative AI for 3D content, particularly X3D content. So our speaker today is Athanasios G. Malamos. Athanasios Malamos is a professor and a rector, the vice rector of Hellenic Mediterranean University in Crete. Since May 2002, he's been assistant, associate, and full professor in the field of multimedia technology and services. He's done quite a lot of work on multimedia, particularly integrating 3D graphics and audio in a comprehensive form in different types of media. You can find his short biography on the webinar page. He's done a bunch. He's had some amazing students do amazing work. His research interests include online multimedia, Web3D, and virtual reality. He's the perfect person to help us understand what's the basis of how do we go forward with these new tools at our disposal. Tanos, thank you very much for being here today.
Thank you, Don. Thank you very much for your introduction and for your compliments and your kind words about me. I'll tell you what, my occupation with AI and 3D content starts exactly when we start with my students to work and research in this area. And this happens some 3 or 4 years before, when one of my students was about to finish her thesis, her bachelor thesis, and go on for master's and PhD, where she is right now as a PhD candidate. So we start working primarily for classification and segmentation on 3D content. And finally, the last couple of years also for generation of 3D content by using AI technologies, mostly deep learning and neural networks and etc. So today I am planning to make a presentation of an overall presentation of all the content and the basis of using AI for 3D content. So my presentation is not going to be very deep into certain kind of algorithms or models, but it's going to lie all over the area of AI for content generation. And I leave the audience and the students usually to work on, especially on what they are interested on. Okay, so we will go on. We will start with some fundamentals and fundamental theories about AI in 3D specific. So generative models are a class of machine learning models, and their primary work is to generate new data. To generate new data means to generate 3D structures, 3D shapes. As we will see later, we can work with voxels or also points, or also with meshes and etc. But in general, all these are considered as 3D new data that they have to be generated. So generative models usually work with data distributions. This is what usually is happening in the cases of that kind of algorithms. Let's see some key features of generative models. First of all, usually, I mean, most of the times are unsupervised, which means that the learning curve is working unsupervised. So they don't require labeled data. Of course, we may have some structures, or we may have some kind of collections in order to train our models. But in general, we don't have to have labeled data, which is, an added value for this case. Creativity can generate completely new samples that never existed before. And also, they are capable of modeling intricate patterns and dependencies in data. Why they are important? They are important because they generate synthetic data for training, sometimes other models as well. And also, they may work as anomalies detectors. There are mainly two types of models, of algorithms. The one which is what we may say as likelihood-based models, statistical-based models, and the other that are likelihood-free models. Both of them, they are using statistics somehow and probabilistic curves in order to extract the outcome. But it has to do on whether the first case optimizes a likelihood function, or in the other case, it doesn't directly optimize a likelihood, but instead is using other ideas. Some examples of algorithms that are likelihood-based models are the variational autoencoders, normalized flows, diffusion probabilistic models, and energy-based models. On the other hand, we have the generative adversarial networks, which are very common and very useful right now, and they are used very extensively. We will start with the last case, the generative adversarial networks. We have a combined network of a combined algorithm of two different neural networks. The first one is working as a generator, and the next one is working as a discriminator. The generator creates synthetic data, and the discriminator distinguishes whether the data created are real data or synthetic data. So the whole algorithm, the whole GAN's algorithm, is working like a min-max game case by using the Nash equilibrium. For example, the generator creates data that are trying to fool the discriminator, and the discriminator trying to understand whether data are fake or real. So the generator creates all the time better and better type of kind of data, of 3D data, and the discriminator is trying to understand whether data are real or fake. Another algorithm, which is in the likelihood based case, is the variational autoencoder, which is a type of deep latent variable model. In this case, we have an encoder, a decoder, and a loss function, Also, it is a structure of different algorithms, um, either neural networks or not. Sometimes they may be functions or even also neural networks to use as encoder or decoder. And we use a loss function in order to verify the data we're producing. In the next slide, you may see an example of how you may use this type of models in order to create 3D data. Assume, for example, that we have a 3D point cloud representing a chair. Each point of the cloud has its own coordinates. Now, latent variables. Latent variables and latent layer in general is a typical case in case of our of 3D data generation, I may say, because the latent vector or latent layer or whatever, it is introduced between the real data and it usually we transform the real data into a latent layer in order to express in a higher complexity something which is expressed in a higher complexity in order to express it in a meaningful form in order to be able to use it during the process. So, for example, when we transform the chair data into a latent vector, then we may introduce things in there. We may introduce things like shape, size, scale, orientation, curvature, or surface details. This layer usually is produced by some kind of neural network structure as well, multi-layer perceptron or something like that, and it transforms the data we have, and here are the coordinates x, y, z, into a 128 vector or into 256 vector or something like that, 1000 also sometimes vector, that inside this vector we have all the information that we underline all the features that may give us a very good expression, a very good description of the data. Now, so the latent variable is something that we will see later in most of the algorithms, and this is because it helps us to express different kind and several and different kind of information into a vector. Now we get this latent vector, and we generate a new point clouds. So we need a decoder that comes from Z, the latent vector, and transform it to a 3D, for example, point cloud. The generated point cloud is similar, of course, to training objects, but it is unique since it is a new piece of information, a new data information. Okay. Another case are the normalizing flows. They are also powerful and likelihood-based generative models that transform simple probability distributions into complex ones using a series of invertible and differentiable neural network mappings. So we have, for example, an invertible transformation, a core idea, a simple distribution, and we are using a function that transforms this simple distribution in a more complex one. Of course, think that we are working with information, 3D information. So we guess that this, let's say, distribution refers to a distribution of points or of something which is, in 3D form, in 3D shape. So we have a distribution of points, for example, and we make more complex distribution by using distributions by using this transformation. This transformation should be invertible in order to be able to go back and forth according to our to our um, outcomes and to according to the error function that we are trying to maximize, of course, to optimize. Now, uh, we are using a certain type of um, a certain type of algorithm to change the variables, to define where if we are close or not to the point where we are expecting to go. For example, if we are shrinking or expanding volumes, this is a metric we can use in order to specify whether our transformation is going to more complex form, but also is efficient enough in order to go to where to lead us to where we are working and we want to go. Flow composition, of course, where composite, simpler, invertible, and differentiable mappings into a more meaningful case. Another type of models, of algorithms, are the diffusion models. The basic idea is to parameterize as a Markov chain and gradually add noise to our input in order to change the distribution. So we are talking also for 3D data where we are adding noise, and by that noise we check all the time whether are we are going to the point we want to go. For example, assume that we are measuring volume of the 3D, or we are measuring, as we said before, and a transformed layer, latent, where we want to evaluate whether the outcome is close enough in order to accept it as data and to start from there as a Markov chain to go to the next step, to the next state. At the same time, we may say that we have to find out a way to add noise in a way that it is reversible, so we can go back and forth by changing the way we are adding noise in order to manage to catch the optimization criteria we are using. Another major family of models are the energy-based models. And these they are working as you understand already. All the likelihood based models are working more or less at the same in the same way. What differs between them is mostly the way we are measuring the optimization criteria and the way that we are estimating whether we are close to the optimization criteria or not. So here we are based in an energy function, and this energy function produces calculates whether we have a case where we have low energy, so high probability of data points. So we will keep whatever changes we have made, or high energy, so low probability, so reject or modify. This is the idea behind the energy-based models. Let's see an example of how they are working for the SharePoint cloud as well. For example, training phase. Okay, we have an energy model that learns an energy function. So we are training through the 3D SharePoint clouds. We are feeding the neural network with a data set of SharePoint clouds, 3D SharePoint clouds, and we are creating, we are training an energy function, and then while testing, if we feed it the system with let's say a point cloud, and if this point cloud gives low energy, then it is a realistic chair. If it produces high energy, is an unrealistic chair. Okay, now of course this is the training. The sampling and generation phase starts with a random point cloud first. So we are starting with a random when we want to generate, okay? Because this is a classification. The first step, the training phase, it is mostly look like a classification. But if you want to generate, we start with a random point cloud, and then with Markov chain Monte Carlo, we are make variations of this point cloud in order to see whether these new variations we are going to lower energy, so we will keep the variation and go on, or we are going to high energy, so we will withdraw the variation and we will come back and create a new variation, and so on. Okay, so after multiple iterations, the point converts to a configuration of low energy, because in every step we choose the variation that give us the lower energy possible. And of course, we expect that the new data we create, the new form we create, will be a realistic chair. Also, features like, for example, how many legs, backrest, seat, and several things like that that are related with the realistic chair we are trying to design has to do with the energy function we created during the training phase. Okay, so it is more or less the typical flow chart of a generative AI algorithm model that is based on likelihood ratio statistics. Now, these are the main, let's say that the most typical cases of algorithms used for 3D generation. If we want to see it again, we will see the variation of the encoders, the normalizing flows. Variation of the encoders, as we said, is a mix of different algorithms that create, encode, and create and encode and check and go on. Normalizing flows, diffusion probabilistic, and energy-based models. And of course, in the case of likelihood-free models, we have the GANs, the generative adversarial networks. Now, I will go on by looking how we can work with a different kind of 3D formats, 3D structures. And first of all are the voxels, of course. So when we want to work with voxels, in the literature, we will see many different kind of AI generations. Voxels in general, as I'm sure that you are familiar with voxels, and voxels are very well and very tight engaged with 3D, with images and generation of 3D through images, through different views, for example, of a 3D, of a real 3D um, image or model, and also how to work with images in order to create 3D. Voxels, the way that they are structured, the voxel representation of 3D, is it looks suitable for 3D convolutional neural networks. Okay, and also it works very well for classification, detection, and segmentation. How we use voxel grids in generation, in 3D generation. Here we are presenting the case of ShapeNets, where we have an input conversion. So we are having a 3D object, and we start with a depth map first, and we transform this depth map into 3D voxel grid. 3D voxels are like 3D pixels, and so it is quite easy to transform a depth map into a 3D voxel grid. Right after, we process the voxel grid with a convolutional deep belief network, which is a neural network, which is multiple layer, and also it is using the latent hidden layer in order to transform the input information, which is the voxels, into into vectors that are that are using higher variables, higher dimensions, in order to express many different information that is hidden inside the voxels. Of course, we expect that the deep belief network, which is, as I said, a multi-layer neural network, will learn the probabilistically reconstruct its inputs. Okay, learning a distribution, because the DBN models the probability distribution of voxels configuration, it doesn't just recognize or classify shapes, it learns underlying likelihood of different 3D structures. Okay, since we have a latent variable, we are not consider, or we're not expecting that we are going to understand typical shapes as we mean in the real life, but instead it is working with likelihood of different 3D structures. And finally, generation. Once trained, the model can sample from this learning distribution, generative, entirely new 3D voxel-based shapes. So, also, the 3D voxel-based shapes are expected to respect the likelihood and the probabilistic form of the generation mostly than shapes or something like that. Okay. Another case are the use of images, 2D images, also single or multi-view images, in order to create 3D structure. We have a case of an algorithm like 3D R2 and 2, where we are feeding the system with images instead of 3D data, like depth map we did before. Right after, we are gating images, and through a neural network, we are transforming the information of the images into a latent vector. And this representation, of course, as I said, is a representation of a vector that embeds inside all the information that can be extracted by the images. Now, right after, from the images, and perhaps with a 3D CNN, as in the case of this algorithm, we make a decoder that converts this information, which is a latent vector, into 3D voxel grid. And of course, the generation, since the model works in latent space, it isn't restricted to reconstructing for input images, but also samples new latent vectors instead of encoding from a real image, which means that since we are using this middle layer of latent vectors, we can insert there also other information as well, and not only geometrical information. For example, you can use text, words, descriptions, and other things, as long as may be inserted in this middle latent layer. Okay. Now, for new data generation, these samples latent vectors can be then decoded into voxel grids, producing a new 3D shape. As an overview of generative rendering tasks with voxel grids, we have inserted here also the early methods and also a more modern methods. In early methods, we have the first of all store high dimensional feature vectors of each voxel. These feature vectors encode the scene geometry and appearance. The stored information is then interpreted into color images using projection. Okay, and that allows the generation of rendered images from voxel-based 3D data. So we are rendering 3D information into images, into renders, okay, by using the voxel features and the voxel properties. In the case of neural volumes, we are using neural networks to predict red, green, blue, and alpha volumes. The predicted volumes are synthesized into images through volume rendering techniques and enables generating realistic 2D images. And finally, the multiplane image, which is treated as a variation of voxel grids, and the 3D space is divided into several deep planes instead of voxels, with each one to be expressed in RGBA image. By reducing the number of voxels along the depth dimension, computational cost is lowered and still supports generative rendering, but in a more efficient way. This is a way that we can render out of voxel grids. We can render information, we can render new images out of a training set. And also, we have the use of GANs for voxel grids. And in this case, we have as you remember, we have the GANs are is a family of algorithms that are not likelihood based, and they have they are working, let's say, a small game theory example with a generator and a discriminator. The generator is creating something which is closer, all the time closer to the real data, and the discriminator try to understand wherever it is real or synthetic. So in the case of generator, we have a dimensional ladder vector to a 3D voxel cube, of course. We know that. I mean, it is typical in all the algorithms, more or less, to work with a latent vector layer, which is usually high dimensional. As I said before, we are starting with 3D data or a voxel data, and we transform them into 1,000 dimension vectors, or I don't know, 500 vectors of dimension of 500 or something like that. So inside this layer, we inserting all the information or the unexpressed information that describes the 3D structure. So describes the synthesized object in voxel space, constructed using a sequence of 3D convolution blocks to handle 3D voxels data. The discriminator tries to understand where it is, if it is real or generated, and usually uses convolution blocks of a certain dimension, 3 times 3 times 3, or 7 times 3 times 3 kernels, and followed by 3D patch normalization and rectified linear unit. These are all things that we are using in deep learning. They are very active things that we are using in deep learning, like rectified linear unit or batch normalization, etc. And finally evaluates the realism of voxel grid. Okay, whether it is real or generated. Now, the encoder uses a similar design like variable or GAN, via or GAN, and maps a 2D image into latent space of the generator, and uses adversarial laws that ensures realism, reconstruction laws that ensures encoder-decoder reproduces shapes correctly, and also the KL divergence laws that contains the output distribution of the encoder. Usually the KL divergence laws is used to specify whether two different shapes, to different curves are close one to the other. Distributions are close one to the other. Of course, the GANs in 3D voxel grids can recover 3D shapes from 2D images, of course. Learned discriminator can be transferred to other 3D downstream tasks. And in comparison to 2D GANs, of course, are 3D convolutional networks, and also encoder added for mapping 2D images into latent space resembling via or GAN. Now, via approaches for voxel grids, encoder-decoder architecture, okay? I remind you that these algorithms are organized into by having three major importance parts: the encoder that is encoding the information, the decoder that is creating the voxels out of the latent layer, and the objective function that tries to understand whether the voxels are in inside our expectations or not. So in this case also, we have many algorithms and many applications in the literature that works with voxel grids and the use of variation autoencoders. And also we have a vector quantized variation autoencoder examples where and the motivation to develop vector quantized variation autoencoder is to use single latent vector for the input, which can produce, to create more complicated latent vector, because the single latent vector can produces blurry voxels outputs that are not very clear. Also have autoregressive modeling. In that case, once the latent space is trained, the transformer is used to autoregressive model to non-sequential data and generative capabilities that can perform shape completion and text-guided shape generation. This is the case as well. Since we are using latent space, we can work also with including in the latent space, in the latent layer, also other information different than the geometrical information that the voxel present. Now, the case of point clouds. When we are working with point clouds, we are, first of all, what we know more or less what point clouds are unstructured sets of 3D points, usually representing the surface of an object. The GAN-based methods for point clouds, we have the distribution, of course, and we have a generator, which is usually a multi-layer perceptron with fully connected layers, at least 5. And also, we have a randomly sampled noise vector to a point cloud of 2000 points. And the discriminator, in that case, may be a point net backbone. A point net is an algorithm that can be used for classification. Point net is also a deep learning algorithm, as I said, and can be used for classification. And here we can use it for discriminator. It is typical into GAN algorithms to have, as I said before, two different neural networks, the first one for generation and the second one for discrimination, for discriminator. Here, as we see in the RGAN, raw point cloud GAN, it is a case in the literature. We have a multi-layer perceptron, as a generator, and we have a typical point net, which is very well and extensively referred into the literature as a discriminator. Another case also is instead of using just a MLP for generator, is to use also a latent space for pre-training an autoencoder, and to use this latent space in order to insert more complicated information into our system than the typical multiple layer perceptron, which is a very simple structure of a neural network. In the case of point clouds, we can use also adversarial autoencoder and also variable autoencoder. As an encoder, there you can see that we can use a point net network, and as a decoder, we can use an MLP network. It is the case as well where in the case of of autoencoders, also it is using two different neural networks in order to make the algorithm. And the first one is the encoder, and the second one, which is taking the information and inserting and transforms the information into the latent layer, and the decoder that takes the latent layer and creates the information back to the user and gives back the information, the 3D data. Okay. And also we are using some kind of losses functions in order to check whether we are close to the expectations, whatever it is. I mean, it has to do with the information, with the algorithm. Now, also, we are using normalizing flow methods like point flow or short flow, where we have models, point clouds as a distribution of distributions, and samples points from a generic prior Gaussian that applies conditional, usually continuous normalizing flow. I remind you just what I said in the beginning of the presentation, that the flow methods, the normalizing flow methods, they are using some kind of generic first of a generic distribution of data. I remind you that we're working with point clouds, so with points in 3D space, unstructured points in 3D space. So we are starting with a prior generic prior distribution, and we are let's say changing this distribution in order to fit to some kind of optimization criterion. Exactly in the same idea, it works the diffusion and denoising methods for point clouds. We are starting with a mesh of points. I mean, with something very general, where we have points and we describe surfaces in that way, and then we start to clear these points, to denoise these points in order to creating something which is the 3D, close to the 3D shape we are trying to fit. Another case of 3D expression are the neural fields. They are very successful ways of expressing 3D as well. Can model shapes of arbitrary spatial resolution, more memory efficient than voxel grids or point clouds, applying standard generative models like GANs is not straightforward. Issues, of course, lack of ground truth data. The problem with neural fields in general is that we don't have enough ground truth data. We don't have enough training data. So we consider that GANs, which is a type of generative algorithms, AI algorithms that are not necessary, that are not using necessarily training data which are labeled. So the data can be unstructured somehow. So this kind of algorithms fits better with neural fields. The concept is that we have a single row neural feeds, don't have ground truth, of course. GANs are applied not directly to the feeds, but in the latent feature space. Of course, always we are using a latent space. Okay, we have an autoencoder, an encoder that maps a set of 3D shapes to latent vectors, can use 3D convolution neural networks or PointNet for the encoder. Decoder is typically a multi-layer perceptron. And the latent GAN training, GAN is trained to generate new latent vectors that resemble those encoded from real samples. The discriminator distinguishes between real latent codes and fake latent codes. hybrid representation. The concept is to improve spatial control and expressiveness. Latent representation can combine voxel grids plus implicit fields. Mechanism, each cell of the hybrid representation responds to a portion of the shape. Latent GAN is trained for these hybrid features. Advantages of hybrid representation. Hybrid is a mixed representation, provides spatially aware generation, letting GAN control detailed parts of the shape more effectively. Side distance field discriminators. So, two types of discriminators for training GANs on neural fields: voxel-based discriminators and point-based discriminators. Okay. And finally, we have the meshes that also are expressing 3D shapes, 3D forms. The meshes have certain problems, and that's why we don't want to work with meshes in general. But on the other hand, we all know that they are very useful in the case of rendering and in the case of presenting the 3D information. Meshes are non-Euclidean structures, so cannot be directly processed by standard convolutional neural networks. And also, vertex connectivity, generating plausible connections between mesh vertices is difficult, which is crucial for realistic shapes. So, how we make generator models for meshes? We have several different kinds of generator models, like multi-chart structure, which is a GAN type. We have structured deformable meshes. So we're using a deformable mesh and we change it in order to create something which is closer to the expected. And in this case, we are using variational autoencoder. We have textured meshes, and in this case, we are using CNNs, neural networks, and of course, autoencoders. We have the polygenes that employs an autoregressive generator with a transformer-based network. Vertex transformers generates vertices sequentially, sorted along vertical axis, and phase transformers that condition or generate vertices predicted mesh faces. Shape assembly uses a sequence of VAE where the decoder is the generator. So this is a quick overview of all the most of, to be honest, of the algorithms you can find in literature on generating 3D 3D information, 3D data out of trained, of course, neural networks, and at the same time, or out of descriptions, textual descriptions, or in general descriptions that are not geometrical. So we all know that AI is doing very well, all this stuff right now. And this is, let's say, the first of a course, of a webinar, in order to start with a subject like that, which is, I may say, huge right now, because it is something, if you will see the literature, it is something that is started less than 5-6 years from now, but it is huge because of the huge interest of the research community that works in this area. Of course, neural networks and all the basic information like deep learning and etc. Is something that it is in the market the last, I don't know, 40 years, 30 years, I don't remember, but it is, it is only in the last decade that we see very respectful outcomes to come after this effort, And we see also that major companies are engaging this area of AI and 3D generation algorithms. Okay, that's it for now.
Professor Malamos, thank you very much. Very deep, very impressive, very helpful. We do have some time for questions if anybody would like to offer them on the audio or on the chat or on the video. Good. While people are pondering, I've got some questions for you.
Yeah. Okay.
So, yeah, and let's see. Can we turn off the share?
Ah, okay. Yes.
And
Okay.
okay, so you've given us a broad survey showing many techniques, and I think this will help us in not getting over focused on one approach or confounded by differing approaches. So maybe a few questions. I'll break it up. Given the variety you've shown, do you expect that for 3D on the web, 3D models, which could be applied in many ways, do you think we are converging on one hybrid technique, or will there be different techniques, different approaches for different goals?
As you can see in the literature, um, different approaches has to do with the application mostly. For example, the voxel approaches I show you, they are more close related to generation of 3D out of images. Voxel are more appropriate in that case. So the algorithms that are developed and they are working with voxels is mainly focused for this kind of applications. So, and they are right now. I'm not sure if it is very efficient to say that okay, we are going to have realistic applications in the web. But with cloud computing and all this effort we are doing in backbones and background computational, I think it is more and more realistic to say that in the future, in the near future, we're going to have real-time applications that are able to create out of 3D images, out of 2D images to create realistic 3D images. Okay, so it has to do with the application. For example, in our case, in X3D case, what we have is sparse meshes or sparse point clouds. So if we want to be more efficient computational, I feel that we have to work closer to points, closer to point clouds. But on the other hand, as we said, meshes are very suitable in order to make lighter 3Ds, to make 3Ds more, let's say, more close to texture and to rendering. So I think that we may see a mix of algorithms that get the advantages of point clouds, which are the computational efficiency, which is the computational efficiency, and not only that, and also to get some features from meshes, mainly the texture-oriented features, and to create texture 3D, upon meshes, upon point clouds, for example, or something like that. But as you can see in the literature right now, the most of the algorithms are using the same structure. I mean, they are using the latent layer, which is including many different types of structure behaviors, structural descriptions, like shape, like volume, like orientation, like whatever. And all these are transformed in this latent into a high vector. Okay, into a vector. Uh, and also they are using one or two mostly different types of neural networks, which are also very well studied. I mean, they are not inventing new types of neural networks, but they are using PointNet, for example, which is a typical neural network algorithm for classification, and a generic multi-layer perceptron in order to make the whole algorithm. More or less, all the algorithms are more or less the same. I mean, they are looking the problem with this in the same way. So, okay, I expect that we are going to have some progress in the near future, in this area, in in our case, in our case, I mean, in the XTD case, I am expecting to have some kind of mix of points and textures in order to overcome the problems that meshes are inserting to our algorithms.
Thank you. Thank
I
you.
saw a question in the chat,
Yeah, please.
but you know.
Doug, you can
Mhm.
join in if you like, or I'll just read it for now to help Tanos give you a moment. If a point cloud resolves to something close to a plane or a sphere, would or could a second process make it into a plane or a sphere or a cylinder? In other words, simplify it.
Yeah. It could happen, but typically, as we said in the course, the algorithms are not working with the real data. They are working with a virtual layer, and so they are not considering. They are considering mostly um, probabilistic space and not exactly geometrical space. That's one of the problems of these algorithms. So, okay, yes, it could happen, but it is something you will see. You will see it inside the whole process. I mean, you have to train it in order to do it.
Yeah,
So, okay, you may train it when once you have a plane, and for example, a point cloud that is a plane,
yeah.
to give it this feature and say it is a plane. Okay, so it is a matter of classification there, but not just like that. I mean, not not because not because it is looks like a plane, but because the virtual layer has this kind of functions of expressions that transform and give this label to our data, a label of sphere or a label of. Now, after you have the label, of course, you can create your own sphere or your own plane. It's okay. You can do it. You can do it. But the first thing is to recognize that it is a plane, to recognize that it is a sphere, to recognize that it is a cylinder. And this is something which is not straightforward. I mean, it doesn't work like our eyes and our senses are working.
Understood. I want to build on the next question. The initial question is for humanoid figures, might SDMnet be appropriate? You've mentioned a couple of others in here, ShapeNet and other 3D generative model approaches. We have a large, well, reasonably large starting point, 4,000 models that are mostly polygonal, and they're in X3D, and they have metadata. And a question we've asked for a while, but not sure just how to start is there an accepted vocabulary metadata set for classifying shapes so that whatever algorithm you might use, whatever tool, you can at least say, well, here's what I'm looking at, and here's what I got, and do the names
Mm.
match?
Yeah, I'll tell you what. If I'll try to answer also to Anita's question as well.
Very good.
Anita, first of all, we may say that metadata information can be inserted in the virtual layer, the latent layer. I mentioned that before. In the latent layer, you should insert, of course, the real data,
Right.
which are the points, for example, X, Y, Z points, okay, and also other information which is not uh, geometrical information, which is not
Right.
mathematical information,
Right.
like the metadata data. For example, this structure is something with color. So you insert
Yeah.
color information. So you are inserting, okay, XYZ and RGBA at the same time in the same layer,
Yeah.
the latent layer, and this is mixing all this information to create the vectors, which are high-end vectors of 1,000, for example, pieces or more. Yeah, coordinates or more. Now, for the metadata, I can see the metadata to work better with LLMs like systems. The large language models like ChatGPT and etc. This is our presentation today, our course today has nothing to do with LLMs. Okay, first of all, they are only algorithms that are not large language model algorithms. Okay, first of all. And on the other hand, if you want to work with text and script and stuff like that, it is perhaps better to work with LLMs. As I said, the AI algorithms we mentioned today can work with other information, auxiliary information in general, but this is not their, let's say, best case.
Yeah.
If you want to work with text, if you want to work with stuff like that, with scripts, with code, yeah, uh, we are we would try to work with LLMs, which are work with text, work with script, work with words, and they are very familiar to that. Okay, so
Yeah.
yeah.
Very good. Okay, so this is the
Don,
perfect.
can I
Oh,
just
please, yeah,
one more
Anita.
question?
Yeah, yeah.
So when you say you're developing these algorithms, do you plan to use these algorithms within your university, or do you see that these LLMs will somehow adopt these algorithms? Because the LLMs already have some LLMs, I mean algorithms for 3D, generative 3D models. So are
Mhm.
they complementing this, or is this in addition to what the LLMs have today?
Mhm. Now we're working with Generation 3D, and Constantina is one of my students is right now here, and she's hearing our presentation, and she's working with that, and I hope that soon we'll have some outcomes. But we're not working with LLMs right now because we consider LLMs as another category, different category on what we focus right now. We focus on generation of 3D points or 3D structures and not on generation of 3D images, 3D views. Okay. To the question that Doug Sanden put in the chat, if we can use LLMs to generate images and then from images, yes, it is possible. It is possible because LLMs have already developed many algorithms in order to to generate images as well as 3D content. But it is a different kind of algorithms. It is not. They have many similarities, of course. I mean, this combination of different neural networks with the one to generate and the other one to try to understand whether it is fake or it is true, and all these ideas are common more or less. But working with text is something different. Yes, you can use LLMs in order to generate image and then to use image in order to create 3Ds. And it is something that happens right now in the LLMs systems you see in the internet in general.
Anita, how was that?
Good, good. My other question was these algorithms that you have, do you have any methodology to include user control and editing? Because based on the quality and realism of these generated models, will there be tweaking allowed?
There are many efforts in the literature, and I said that you can insert this user control into the optimization functions, the error functions, and also you can insert, for example, the quality of the outcome has to do with how many points you are creating and how dense is your outcome, for example. And so you are describing better the 3D shape. And on the other hand, you may insert, as I said, textual, let's say, information or humanized information. You can insert into the latent layer and include it in the vector in order to be able to encode all this information inside the vector and create something which is more close to user requirements or needs. I don't know, but we are in the beginning right now. Right now, we are working with the algorithms. We are creating data. We're evaluating the algorithms because, as I said before, it is something. I mean, neural networks and deep learning is something we're working the last 40 years. I don't know. I was a student, and I had a course for neural networks when I was a student. But on the other hand. It is the use of all these algorithms. It is in the literature the last 5-6 years, I don't know, 7 years or something. So we have many things to do because we are not we are not in the beginning in the sense that we are doing slow steps. We are doing very fast steps, and we are running right now. Because of the companies as well that are engaged, like OpenAI and all these companies. But on the other hand, we have to work with so many information, and we have to evaluate all this information in order to clarify what is useful and what is not useful.
Like Don mentioned, we have 4,000 models done in our
Correct. So
repository.
far.
I mean, we can
Yeah,
help.
okay.
We can help you with some testing.
Yeah, I think we can use this information as a data set, but mostly for the problem with X3D. It's not a problem; it's a feature, as far as I know, because I know X3D from when it appears, and I'm working with it. The feature of X3D, which is a problem somehow, is that we have a mix, and that's a feature, as I said. We have a mix of vocabulary, script description, and at the same time points and meshes. And so in the same 3D, we have different types of expressions of 3D information. We have the textual information. So that's why I guess we need something mixed. I mean, we need to work with the typical algorithms of points or meshes for the information that is included as a mesh or as a point set, and at the same time to work with the LLM techniques for the textual information, which is not only metadata, but it is script as well. So we have very interesting things to do there. I mean,
I think you've just described our motivation for getting coherent about shape vocabularies, because X3D can do polygonal or point-based or voxel-based. We have all three of those representations. So if we can label them accordingly, and say, when is a chair, is a chair, is a chair, and what is a chair made up of? Oh, then we can test that. We can compare, it's
we did
early.
it.
We've got to do more experimentation.
If you go to the Web3D presentations, a couple of years before, I don't remember, 24 or 23, I don't remember exactly, we did some examples with AI classification and X3D models at the same time. And we were using PointNet in that case. And also, one thing that it is very interesting, and I think that our audience right now may evaluate this, is that we train in a supercomputer, of course, but after training, the neural network was running in a JavaScript code inside the web page, in real time. So it was very interesting to see that it is very easy, once you have trained the algorithm, to use it in JavaScript in real time in a web page. So it's very interesting to see that. Okay.
Yeah, we're starting to see that. Well, your
Yeah.
students certainly have no shortage of wonderful challenges right now. Here, could I offer a possible test asset that will integrate all the other tests? Okay, if we say that 3D geometry are models, we can visualize them, but we can also 3D print them. And those 3D models correspond to 3D shapes in the real world. Well, if we can print them and then we can scan them and we could say, can I recognize that? Did I get the same thing? We have a real world round trip test from the virtual, the model, the geometric to physical reality and back again. And so, did I leave anything out?
I don't know.
It's everything and everything. So
Have-
I think this is very promising what you're showing us today, Tanos.
I hope in the near future, I mean, in the next conference, Web3D conference, to have my student present more things in generation, in 3D generation, and we are working as well for sparse 3D data generation, which is closer to Web3D technology, because the dense information is not very web friendly, as you know. So we need some sparse, some light information. So
Yeah,
we are working
right.
on light information, and we will see what our research will give back to us, and if it is something very useful. If it is something we can present, we will do it in the next Web3D.
Outstanding. We had, let's say, one more question from Doug. You partly answered. The ongoing, 30-something years of Web3D conferences is a huge amount of material that's very focused that can be applied here. Doug's question is, are there any books you can recommend, uh, Dr. Malamos, for all of the things you've described that will help people
Yeah,
understand?
there are many, not exactly books. There are some books right now. I mean, books written in 23 or 22 but the problem with books, I mean, in cases of research that is going so fast, the problems with books is that are, there are a little bit, back. I mean, it is only for fundamentals, not for what is running right now. Instead of books, I would suggest to look on surveys which are more appropriate in this case, since every year we have a few surveys that give all the new information. So you can start with surveys back in 90 or 18 2018 or 2019 and start with these surveys in order to understand what is going on, and then to go with new surveys that comes every year and have all the new information inside, because it is huge. I mean, the information is real huge. It was very difficult for us to stop and let's say decide which to include in this course and which is not included. It was very difficult, and I'm sure that something is missing. I'm sure about. But anyway, you have to make some kind of classification of the information and to discuss and to decide which is going to be presented and which is not.
Excellent, excellent advice. Well, on behalf of everyone present, but also those watching in the future, you've been very generous with your time and your knowledge. Thank you for sharing your vision of the future based on much fundamental work on the present. So, Tanos, thank you. Is there any one last thing you might like to say today?
No, thank you very much. I'm enjoying very much your company, and I'm enjoying very much this, this consortium that I'm working with you the last, I don't know, 15, 20, I don't remember how
Yeah.
many years. And I'm enjoying all this work we're doing together. I hope that in the next, couple of months, to be able to give some more detailed information of what is running right now, and to focus, of course, to what our laboratory is has its own challenges, and we have to follow these challenges. So thank you very much for the opportunity, and I'm looking forward to seeing you and work with you again.
Thank you. Let's all join in applause for Professor
Thank you.
Malamos.
Thank you. Thank you.
Thank you. All right. Take care. We'll see you guys at the next webinar.
Yes,
Bye.
we'll have the recording posted soon, right?
Yes,
Thanos?
correct.
So the recording will be online, so we can go back to this presentation anytime.
Yeah, and I'm gonna send you right after the last presentation, because it has some variations from the
Sure.
one I sent you a couple of days before. Okay,
Okay.
thank you very much.
Thank you.
Very
Thank
good.
you.
All right. Bye,
Bye
everyone.
bye.
Bye.
You want to halt the recording, Anita?
Mm-hmm.